your cameras on if you'd like to. And as that notice says, the first part of the meeting will be recorded, so the main presentation will then stop the recording after that ends, so you can feel free to be as uninhibited as you like with asking Pascal lots of difficult questions. And yeah, so without further ado, so it's a real pleasure to introduce today's speaker, Pascal Mamassian. So Pascal was originally trained in engineering, and then he moved into cognitive science with a master's in cognitive science in Paris and a PhD in experimental and biological psychology at Minnesota, in University of Minnesota in USA. And he then worked at the Max Planck Institute for Biological Cybernetics in Tübingen and at NYU before moving to Glasgow in the UK as a lecturer and then senior lecturer, before then moving to where he is now, which is as a researcher, CNRS researcher in France. And he's now the director of the Laboratoire des Systèmes Perceptifs at the ENS, and has as many of us will know, has a wide range of research interests in visual perception broadly construed, including a focus on Bayesian modeling, a variety of perceptual phenomena. And more recently, and partly how I got to know Pascal, was through his growing interest in confidence and visual confidence. And he's doing some extremely innovative and exciting research on metacognition with his group in Paris. And it's a real pleasure to have him speak to us today at the Conscious Club on some of that recent work on visual confidence. So Pascal, take it away. The floor is yours.
Thanks a lot, Steve, for the introduction. It's a great pleasure to be with you today, and I shouldn't have done that. I'm going to share my screen. How's that? Can you see my slides? So as Steve has mentioned, I don't actually work on consciousness, but it's still great to be part of this seminar series, which is very well attended and very impressive. As Steve mentioned, I'm mostly interested in visual perception, and I'm coming from a psychophysics background. So you will see what psychophysicists have to say about visual decision making. And also all of the modeling work that I'm going to present today is very much influenced by the main framework of visual processing, which is called a signal detection theory. So it's really a talk about modeling, but I hope you will still, even if you're not interested in modeling, I still hope that you're going to be interested in some of the questions that we are asking in our group. Before I start, I should mention that this work was done in collaboration with Vincent de Gardel, who was a postdoc in the lab a few years ago, who is now a PI at the Centre d'économie de la Sorbonne in Paris. So the fundamental question that we're addressing in this talk is, why did the chicken cross the road? And there are multiple answers to that question. One answer is that because the chicken saw that there was no traffic, but one more interesting answer to that question is because the chicken felt confident that there was no traffic. And it's not just sufficient to be able to detect or recognize or identify objects in the visual scene, but some of us have the ability also to reflect on our perceptual decisions. And this is really important in situations like this. This is an example of a road traffic in Mumbai. And I always, whenever I show this video, I have to say that I could look for these videos for hours, and I don't know what kind of psychiatric disorder this reflects to, but anyway, in cases like this, this is a good example of what visual confidence is good for, because being able to judge the validity of our perceptual judgment could help us engage in a risky business, just like in road crossing, allocate appropriate resources to a task, and that's going to be important for perceptual learning, improve our model of the world, and that's within the framework of predictive coding, appreciate whether and how we can control the environment, and of course this is linked to a sense of agency, and communicate a graded judgment to others. That's going to be important for group decisions. So there are multiple examples of meta-perception, such as confidence judgments. Of course, confidence is maybe the most well-studied aspect of metacognition in the realm of perception. But there are multiple examples. In particular, there are examples of, and it's important to maybe separate type 1 and type 2 judgments. Type 1 judgments are the one that we're all familiar with in perceptual judgments. These include object detection, color identification, motion direction discrimination, size estimation. And in contrast, the type 2 judgments would be things like confident judgments, but also possibly also the familiarity feeling that we have in recognizing a face, the aesthetic appreciation that we have in reevaluating a painting in a museum, or the affective evaluation that we have based on some perceptual decision. All of these type 2 judgments are based on some of our own perception, but they also have a reflexive aspect. They reflect a self-monitoring or self-control of our own perception. There are multiple ways to measure confidence. By far, the most common way is to use confidence ratings. And the experiments will look something like this. You present a stimulus to participants. Participants make a decision on that stimulus. And then on the second task, they are being asked to rate the validity of that decision. The other methods have been developed, especially in the animal world, in the animal cognition world. For instance, a classical method in primate research, non-human primate research, is the opt-out paradigm, where you present a stimulus, and on half of the trials, the monkeys would be making a decision on that stimulus, and they would get a reward if they are correct on that decision. But on the other half of the trials, the monkey would be presented with an opt-out option, and if it chooses that opt-out option, it would get a small but sure reward. And the proportion of times that the monkey is choosing that opt-out option is then a signature of metacognition. In yet some other animal models, especially in rodents, there are methods based on response times, waiting times. So for instance, a rat would be perceiving a stimulus, making a decision on that stimulus, and if the rat is correct, it would expect a reward, and the amount of time the rat is willing to wait for that unsure reward is going to be also linked to metacognition. And more recently, in our lab in particular, we have been very much interested in yet another way of measuring confidence that we call confidence false choice, and I'm going to come back to this with some practical examples. But very briefly, this confidence false choice consists in presenting a stimulus. Participants make a decision on that stimulus. Then we present a second stimulus. Participants make another decision on that second stimulus. And then we ask participants, on these last two decisions that you have just taken, which one do you think you're more likely to be correct? Is it the first one or the second one? And then we repeat that process. We present another stimulus, they make a first decision, another stimulus, second decision. And every two decisions, we ask them, on which of the last two decisions do you think you're more likely to be correct? These different methods have been used extensively for more than 150 years in the literature. confidence rating, waiting time for reward, the opt-out paradigms. It's fair to say that not all of these methods have been having the same kind of success. But I'm here to quite convince you that this confidence false choice is also interesting. So the purpose of the talk today is to talk about a generative model of confidence that is based on signal detection theory. This is where I'm coming from. And let me list some of the desired features of the model that I'm going to describe. First, it should be able to account for the different ways you measure confidence ratings, of course, but also confidence false choice. And in the confidence false choice, one interesting aspect of this method is that there are no confidence criteria, there are no confidence boundaries between different confidence levels. So some of the models that have been proposed in the past are really focusing on this confidence boundaries and maybe adding some noise to the confidence boundaries. This becomes non-relevant for this task, for this confidence false choice. Another aspect is to try to be clear on what we want to model when we say that confidence is a re-evaluation of the validity of our decision. Do we actually mean that we are evaluating the correctness of our decision or something else? I'd like to argue that correctness is not something that people do or even should be doing. And if you accept that, then you have to look for some alternative aim, an alternative objective for what confidence is all about. And what I will maybe suggest is that people are evaluating the ability to judge how self-consistent they are. And in that process, we can define one particular way of, one particular aspect of the confidence bias. There are different confidence biases, but one of them is reflecting a misestimation of sensory noise. An overconfidence in that case would be an underestimation of the sensory noise that people have. A third objective would be to differentiate primary and secondary sources of confidence evidence. The primary source of evidence is what every single model of confidence have, which is that by default, you might want to assume that the confidence is based on the same information that was used to produce your perceptual decision in the first place. So perceptual decision and confidence might be using the same evidence, the same kind of variable in your brain, but you might be able to use some alternative secondary sources. I'm not saying that you are, but if you want to test the hypothesis that maybe you are using these alternative sources, you want to have a model that has these two options to test that you are not using it, say. So in our model, we have one parameter that is taking care of this dissociation between primary and secondary sources that we call confidence boost. And finally, we want to define a measure of confidence efficiency really at the confidence level, at the type 2 level, rather than being stuck in the type 1 level, the type 1 level being the perceptual decision level. And classical efficiency measures in the literature based on meta D prime are really based on that type 1 level. So that's one of the features of the model that we propose. So I've been talking a little bit about the confidence false choice paradigm. Let me give you an example of this paradigm from an experiment with Vincent de Gardel. This is an experiment where participants saw some random dot motion. The dots were moving, say, to the right, mostly to the right, but each dot was drawn from a distribution of directions. The direction the distribution had a mean direction that could be to the right, but maybe slightly upward or slightly downward. And that was your task, to determine whether the mean direction of the dots was slightly upwards or slightly downwards. And then that distribution also had some some variance, some stimulus uncertainty. That's your perceptual judgment, whether the motion moves to the upper right or down right. For technical reasons, we actually presented two of these stimuli on either side of fixation to avoid eye movements, but we can just focus on the left-hand side of the stimulus. And the confidence force choice experiment would look like this. You present a first stimulus. On that first stimulus, maybe the participant is going to respond that the motion is moving upward. Then you present a second stimulus. Maybe on that second stimulus, the participants are going to respond downwards. And then we ask them, on the last two decisions that you have just taken, do you think that you were more likely to be correct in the first or second decision? And maybe on that particular trial, people were responding that they were more confident on the first decision. Participants were tested over a range of stimulus strengths, that deviation away from horizontal, and two stimulus uncertainties. So you can look at the type 1 perceptual performance in this task. This is the psychometric function, where the x-axis is the orientation, that deviation away from horizontal. And the y-axis is the proportion of time that participants responded upwards in this motion direction. For the low variance of the dots first, so you have a nice psychometric function. If you increase the variance of the dots, the psychometric function is now becoming a bit more shallow. It's a bit more difficult task because the range of the dots motion is larger. Now, what you can do is take the same trials, but given that on each judgment, you had to decide whether that judgment was the confident one that you were in a pair of judgments. That was the one that you were confident to be correct. And there was another one that automatically became, you were less certain to be correct on that second one. So you can divide each trial and then replot the same data, depending on whether that particular judgment was chosen as being the confident one or declined as being the confident one. So it's really replotting the same data, but by labeling them as confident chosen or confident decline. And you can refit this function, and you can see that the green that is corresponding to the chosen confidence judgment now has a steeper slope, indicating that you are better on these trials that you have chosen as being confident. And that's really a signature of your confidence judgment. If you are not able to reevaluate your own performance, then the green and the red curve would be completely overlapping the original gray curve. And this is also happening for the high variance condition. So that was really the way that we were first analyzing this data with Vincent. But I'm going to show you at the end of the presentation another way to look at these data. So the first the first objective of our model was to decide whether or the second one actually. The second one was to decide whether confidence was really an evaluation of our perceptual decision being correct. Is correctness the right thing to do? So let's take a very simple perceptual judgment. Here is a Gabor patch that is oriented mostly vertically, but on some trials, you might have slightly leftward or slightly rightward tilt. And this is your task. You have to decide whether that stimulus is tilted to the left or tilted to the right. What you can do is present the stimulus at different orientations, look at the fraction of times over repeated trials, the fraction of time that you are going to report that Gabor patch is tilted to the right. And maybe for any particular reason, maybe because your head is not perfectly upright, but maybe slightly tilted, you are going to have a slightly shifted psychometric function. In this case, you are responding that the stimulus is oriented to the left when it is physically vertical. So you might have a sensory criterion that is non-optimal. It should be at 0, but it's, in this case, shifted to the right. This has an effect when you replot the psychometric function as a function of the probability of being correct. now you have like this big discontinuity in your psychometric function, reflected by the fact that the sensory criterion is a bit shifted to the right. There's another way to plot that function. Instead of plotting the probability of being correct, you can plot the probability of being self-consistent as a function of the stimulus strength. And by self-consistency, what I mean is the probability of perceiving the same thing if you are to present the same physical stimulus over and over again. So if I present that physical stimulus over and over again, I have a probability larger than 0.5 of responding rightward, and that's going to be my self-consistent judgment. That's a rightward judgment for that stimulus. But for that stimulus here, most of the time I'm going to respond leftward, and my self-consistent judgment for that physical stimulus is going to be left. It's going to be incorrect, but it's going to be left. And therefore, my probability of self-consistency is going to have a continuity curve. So that has an effect on our definition of confidence, which is usually taken as the probability of being correct, given our percept and some evidence. If you reject this idea of aiming for correctness, then you will have to define confidence as the probability of, say, being self-consistent, given your percept and some evidence. And this has some practical applications, in particular in this particular example of adaptation and after effects that I'm sure you're all familiar with, but I can help having a small demonstration of this because it's a nice demonstration. If you fixate, even if you have seen color after images, you might want to look at this stimulus also. If you fixate the black cross in the center here for a few seconds, then I'm going to replace this image by another image. What I'm going to ask you is to keep looking at the black cross for a few seconds, even after I have replaced that image. Okay, so I'm going to replace that image with another image now. Keep fixating the black cross. What you should experience is an after image, a negative after image. Whenever a green was presented, now you should be perceiving some pinkish color. So you perceive the complementary colors of green, which is red, yellow that is blue, blue that is yellow, and red that is green. But if you have fixated in the center, you might have experienced slightly different after images on the top and bottom. Maybe the top one was, the after image was a bit stronger, maybe it was lasting a bit longer also, even though the background color of this test image is exactly the same. This actually, I won't have time to go into the details, but this indicates that you have adaptation at multiple levels in your visual system, not just in the retina where you have this color ponency ganglion cells, but also the level of the cortex. That top part here that has closed contours is really being processed by the cortex. So that shows that the cortex is being involved in that very simple demonstration. And once the cortex is being involved, this probably will have an effect on everything else that you're going to perceive afterwards. And maybe that's going to also have an effect on your confidence judgment. So this is what we tested with Baptiste Casio. What he did was basically the same demonstration that I just showed, where you have a section point, you have a brief adapter that is slightly red or slightly green. Then you present a test stimulus that is mostly gray, and you ask people to report whether they perceive that test stimulus as reddish or greenish. In alternative trials, you also have another task where you present now a second stimulus, which is an oriented grating. So you adapt to that grating, it's tilted to the left or to the right for half a second. Then you present a mostly vertical grating, and you ask whether that vertical grating is slightly tilted to the right or slightly tilted to the left after this adaptation. And after each of these judgments, the first one might be a color judgment, the second one may be an orientation or the reverse. you ask which of these two judgments you think you're more likely to be correct. Was it the first one, which could be the orientation one, or was it the second one, which might be the color one? When you look at the results of this study, here is the perceptual decisions, where the x-axis here is the color of the test stimulus, the color of this particular image here, going from red to green. And the y-axis is the proportion of time that people are responding that the test stimulus is green. And you have three curves here corresponding to the three types of adapters. In black, when there is a gray adapter, in red, when the adapter is red, and in green, when the adapter is green. This is just showing that you have the classical negative after image in this experiment, where when you adapt to red, then you have a tendency to report that the exactly gray stimulus is perceived more greenish. So you have this shift of the psychometric function corresponding to a negative after effect. Now, if you look at the proportion of time that you choose either the color judgment or the orientation judgment as being more confident as a function of the different color of the test and the three different conditions of the adapter, you also witness a shift of these functions by the exact same amount. So that confidence is closely following these biases. And you can also look at the reaction times to make these perceptual judgments. And again, you have a shift that is by the exact same amount as the perceptual judgment and the confidence judgment. So the perceptual decision, your confidence, and your reaction times nicely follow the same trend. The main message, if there is one message in this presentation, is really to try to find a way to differentiate primary and secondary sources of evidence, of confidence evidence. So let me spend most of my time on this particular point here. So we start with the classical model of signal detection theory, where any perceptual decision is taken based on some sensory evidence that is coming from the physical stimulus corrupted by some sensory noise. So you make your perceptual decision based on some sensory evidence. So just, it looks natural to use the same kind of philosophy to model confidence judgments that are based also on its own confidence evidence. And by default, again, the idea would be that the confidence evidence is exactly the same. It's just a duplicate of your sensory evidence. So your confidence judgment and your perceptual decisions are based on the same information. And that's the case of the ideal confidence observer. The ideal confidence observer is using exactly the same information for the perceptual decision and the confidence decision. But you can have a different idea about how this confidence judgment is coming about. Instead of having using the same information as for the perceptual decision, you might think that it's using a completely new information, completely independent of the sensory evidence. That in this case would be a bit absurd to think that there's no noise between the physical stimulus and the confidence evidence, but that's just like an extreme upper bound view of how your confidence decision might be taken based on some completely alternative second look at the stimulus just for the purpose of that confidence judgment. And that defines a super ideal confidence observer. That super ideal confidence observer is based on some confidence evidence that is just a novel estimate of the stimulus, not corrupted by any noise. Of course, any reasonable model is going to be corrupted by noise. And the classical way to model noise in confidence judgment is to add some confidence noise on top of the sensory noise after the sensory evidence has been extracted for the purpose of the perceptual decision. So by the time you take your confidence judgment, it's based on some confidence evidence that has been corrupted twice by noise, once by sensory noise, and second time by confidence noise. This is really classical way of measure of modeling confidence noise. But that framework is characteristic of you are still reusing the same information as the one that you use for the perceptual decision. You just corrupt it by more noise for the purpose of the confidence judgment. Now, if you combine these two ways of seeing how confidence evidence is coming about, you have a primary way of extracting evidence from the sensory judgment, and a secondary way coming from the physical stimulus, from a second look. And there's maybe a trade-off between these two primary and secondary ways of extracting the confidence evidence. And the way we model this trade-off is by one parameter, the confidence boost parameter that we call alpha. So our model really has two main parameters: this confidence boost that is looking at the trade-off between the primary sensory evidence that's used for the perceptual decision and the alternative secondary estimate of the stimulus just for the purpose of the confidence. That's the confidence boost parameter. And the second main parameter is this confidence noise, that is this additional noise above and beyond the sensory noise that has been already used for the perceptual decision. So I really want to clarify these two parameters and to maybe give you some intuition about how these two evidence, the sensory evidence and the confidence evidence, co-vary. So the sensory evidence, again, that's the one that is being used for the perceptual decision. The confidence evidence, that's the evidence used for the confidence judgment. And really these two, the sensory evidence and the confidence evidence, co-vary. And it's really important to try to have an intuition for how this covariation is coming about. And this is also very much related to the work of Steve Fleming with Nathaniel Dow. So this covariation defines a joint distribution that has a mean, and importantly for us today is having also a covariance matrix. And you can derive exactly in a closed form solution what this covariance matrix is based on this very simple signal detection way of modeling confidence. I mostly talk about two parameters in the model. That these are the main parameters, but there are also some other parameters that I won't talk about today. But just to give you some appreciation of how this covariation is about, in the ideal confidence observer case, where you use exactly the same information for the perceptual decision and the confidence decision, then you have a one-to-one mapping between sensory evidence and confidence evidence. So if you look at the covariance matrix, you can see that it's a singular matrix. The determinant is 0, so you don't cover the whole space between sensory evidence and confidence evidence. That's one first extreme version of the model. The other extreme version of the model is the super ideal confidence observer. Remember that the super ideal confidence observer is using a new look, a second look at the physical stimulus just for the purpose of the confidence, independently of what you have done for the perceptual decision. So in this case, your confidence evidence is going to be a constant, and it's going to be varying with the sensory evidence. You can take that super ideal confidence observer, add a bit of confidence noise, and you obtain this this diagonal matrix here now for the covariance matrix, indicating that you have some independence between the sensory noise and the confidence noise. Okay. So I think it's an interesting project to try to decide whether your confidence evidence is mostly based on some primary information, the one that you use for your perceptual decision, or also includes, or maybe purely is based on some parallel secondary confidence judgment. The problem is that it's difficult to separate this primary and secondary confidence evidence. It's difficult to estimate this confidence boost parameter that I was talking about. The problem is coming, and that's what we can call the confidence parameter indeterminacy. The problem is that there's a fundamental ambiguity between the main two parameters of normal, the confidence boost and the confidence noise, such that in a typical confidence rating experiment, where you have only two possible stimuli in the world to be discriminated, and where your confidence is based on this, is judged to be either high or low, then it's completely impossible to differentiate the confidence boost and the confidence noise. Let me try to give you an intuition for why this is so. So again, this is the covariation between the sensory noise and the confidence, so between the sensory evidence and the confidence evidence. In this example, the self-consistent perceptual decision is right. So most of the decisions here are to the right of the sensory criterion. So most of the decisions here are blue. Blue correspond to a, say, right for decision. So you can take now the confidence evidence, place a boundary on that confidence evidence variable so that you divide your confidence evidence between high confidence and low confidence. And you have to be careful to separate the cases where you are self-consistent, but the response is to the right, and from the cases where you are self-inconsistent, where the responses are to the right of your, where the sensory evidence was to the left of the criteria. So that you have two probabilities of having high confidence, two conditional probabilities of being high confident. Probability of high confidence given that you are self-consistent. This is sometimes called the type 2 heat rate, and a probability of being high confident given that you are self-inconsistent. This is sometimes called the type 2 false alarm rate. Okay, so based on that single location of the confidence boundary, you can define two conditional probabilities of being high confident, depending on whether you were self-consistent or self-inconsistent. And these two conditional probabilities, you can plot one against the other, and that defines a type 2 ROC curve, receiving operating characteristic curve. And it's a very important way of plotting the information to look at some sensitivity measure of confidence. Now, because you have a single boundary, you have a single point on that type 2 ROC. And the issue is that you can obtain the same point on that type 2 ROC from multiple combinations of the two parameters of the model, from the multiple combination of the confidence boost and the confidence noise. That's why I call that parameter indeterminacy. So as an illustration of this, the black is the original curve that I obtained from simulations of one particular pair of confidence boost and confidence noise. And in green, you have another type 2 ROC that is coming from another pair of confidence boost and confidence noise. What I'm going to show now is some animation where I'm going to change the pair of confidence boost and confidence noise such that and adjust the confidence boundary so that I always get the same type 2 heat rate and type 2 false alarm rate. And I'm going to plot the pair of confidence boost and confidence noise that are adjusted to always get this same value here on the type 2 ROC curve. So here's another pair, and you can see that I can swivel my type 2 ROC curve around that single point here, but with different confidence boundaries for the different scenarios of different confidence pairs. Along the animation, you have seen that I was traveling along a family of pairs of confidence boost and confidence noise. This define a curve here in this space. I can also do the same exercise for the ideal confidence observer. Again, the ideal confidence observer, that's the one where you're using exactly the same information for the confidence, for the perceptual decision and the confidence judgment. And I can also find different pairs of confidence noise and confidence boost that satisfy the same single constraint. And from this exercise, what I can do now is to look at the location where these different curves cross the upper part of my plot between confidence boost and confidence noise. The crossing, that is the confidence noise that corresponds to a confidence boost of 1. I can call that the equivalent confidence noise. And there would be an equivalent confidence noise for the ideal observer and an equivalent confidence noise for the human observer. And if I take the ratio of these two things and I square them, just to be consistent with the ideal observer literature in perception, I define a confidence efficiency. So now I have, what I have done here is this exercise was useful to create an objective measure of confidence efficiency that is really anchored in a type 2 space of my confidence noise and confidence boost. Again, this confidence efficiency measure is defined at the type 2 level, where I have looked at the family of equivalent confidence boost and confidence noise that produce the same confidence ratings. And I look at the where this family of curves cross the confidence boost at 1. This defined my equivalent confidence noise, and I take the ratio of these equivalent confidence noise for the human observer and the ideal confidence observer, and that defines the confidence efficiency. And this defines not only cases where you are worse than the ideal confidence observer, that would be the part on the lower right, but also better than the ideal confidence observer, that's the upper left part. So that's still the problem. The problem is still that we have this ambiguity between this trade-off between the confidence boost and the confidence noise. So far, we've been using it to define the confidence efficiency because we have this whole family of curves. We set one particular value of confidence boost of 1 to say, well, this is a nice level to define the equivalent confidence noise, and that's how we defined a confidence efficiency. But we still have a problem. But there are solutions to that problem. I'm going to give you 2 quick solutions. One using confidence ratings, as long as you have more than 2 confidence degrees, and the second one is to use the confidence force choice. So let me go back to this plot where I'm plotting the confidence evidence against the sensory evidence, and where I have a single confidence boundary that defines confidence, the type 2 hit rate and the type 2 false alarm rate for the self-consistent and self-consistent perceptual decisions. And having a single confidence boundary, you have a single point on that type 2 RC curve. And again, you have some ambiguity because you have other pairs of confidence noise and confidence boost that also go across the same point here. But now if I have more than one single confidence boundaries, then I have more points on that type 2 RC curve. And therefore, I'm really constraining now that curve completely. It's true in theory. In practice, it's still difficult because if I go back, you can see that the other curves were the green, for instance, was very close to the black. So even having multiple points on that curve is, in theory, giving you enough power to distinguish the 2 parameters, in particular, extract the confidence boost parameter. But in practice, it's going to be very, very difficult. And therefore, you will need a lot of trials, for instance. So we have what we have done is to reanalyze some examples in the literature. We chose more or less randomly some papers from W. Ranev, confidence database. This is actually one of his papers with Bang and Shekhar, where they looked actually, I won't go into details of that experiment. It was a perceptual learning experiment where they looked at metacognitive efficiency in different ways. In this particular plot, where here it's an example where they looked at learning within a block of trials, within 97 trials in one single block across multiple participants. They looked at the efficiency, the confidence efficiency within that block of trials. And what they analyzed is the M ratio, which is the meta D prime over D prime. That's a classical confidence efficiency measure. And what they found, which was interesting in that paper, was a decline of the metacognitive efficiency, the M ratio, within the block of trials. What we have done is to reanalyze the same data, but now in terms of the confidence efficiency measure that I just defined, which is the ratio of the equivalent confidence noise between the human and the ideal confidence observers. And we find more or less the same trend, the same downward trend. And indeed, a very high correlation between the confidence efficiency and the M ratio. It's not linear, probably just because we use a square in our efficiency measure. But otherwise, we are measuring the same thing, which is reassuring. But we can go one step further and ask whether we can dissociate the confidence boost and the confidence noise parameters in this study. Indeed, there is an increase of the confidence noise that is explaining the decrease of the confidence efficiency. So, of course, there's going to be more confidence noise within that block of trials. But at the same time, we can look at the confidence boost. And it seems to be, although that experiment was not done for that purpose, but it seems to be that at the same time, there was an increase of the confidence boost. So maybe the participants were changing strategy in using the information in the stimulus for the purpose of making their confidence judgment. At the beginning of the block, maybe they were just monitoring more or less what the information that they were using just for it was equivalent to the stimulus, to the information that they were using for the perceptual decision. But as the block of trials went on, they were maybe better able to go and get some additional information on top of just the information that they were used for the perceptual judgment. A second way of beating the curse of the confidence parameter indeterminacy is to use the confidence force choice paradigm. To give you maybe an intuition for why this could work is because in that paradigm, we don't choose just a single difficulty level. We just don't choose like a single pair of stimuli, positive and negative relative to a reference. We use a full range, the full range of stimulus difficulties to get the full psychometric function of those of participants. And now, in that confidence force choice, the probability of choosing, say, the first interval will, as being more confident, will depend on the stimulus strength in the first interval, the stimulus strength in the second interval, the perceptual decision in that first interval, the perceptual decision in the second interval. So that, for instance, if you look at the interval strength in the first interval, the probability of, and also the interval strengths in the second interval in different colors here. For the case where your first decision on that first interval was rightward, the second decision on that second interval was leftward. This defines a whole family of performance curves from which you can look at the probability of choosing the first interval as being confident. And you have that for that pair of perceptual decision, but also for all four pairs of perceptual decision. What I'm saying here is that you have a lot of different ways of measuring the probability of choosing the first interval as being the confident one for multiple stimulus strengths and multiples in the first interval and in the second interval, and for multiple perceptual decisions. So that allows you to have a lot of ways to measure your, to constrain your model. and you can have a very good parameter recovery. And to look back at that experiment with Vincent that I explained at the beginning of the presentation, we can reanalyze these data looking at confidence efficiency, where 0 would mean no metacognition and 1 would be a metacognition that is equivalent to the ideal confidence observer. For that particular experiment, we have an efficiency of 0.5. But we can, interestingly, we can try to split that confidence efficiency into the confidence noise and the confidence boost. The confidence noise is 1, which is equivalent to the same sensory noise in a sense. And the confidence boost parameter is close to 0, which indicates that you are using more or less the same information for the perceptual decision and the confidence judgment in that experiment. If it were 1 instead, you would be using some alternative evidence in that experiment. And finally, in that experiment, you can also have a measure of confidence bias. That would be, in this case, it's an overconfidence for the high variance, and that's a measure of your underestimate of the sensory noise for the purpose of making the confidence judgment. But I didn't have time to really define the confidence bias in our model, but I just wanted to show that you can also extract also a measure of confidence bias in this kind of paradigm. So to conclude, we have presented a generative model of confidence that has 2 main parameters, confidence noise and confidence boost. There is a fundamental trade-off between these 2 parameters that leads to some parameter indeterminacy, but it also allows us to define a novel confidence efficiency measure. And the nice thing about this confidence efficiency measure, in contrast to the M ratio, for instance, is that it's really anchored at the type 2 processing level. Estimating that confidence boost parameter is important because it is the one that allows us to differentiate primary from secondary confidence evidence. And this confidence boost can be estimated, that is, this parameter indeterminacy can be resolved if one uses either a confidence rating paradigm with more than 2 confidence levels or the confidence choice paradigm. And with this, I'd like to thank the funding agencies that allows us to do our work. And we've put some MATLAB code on GitHub. So far, it's only on the confidence first choice, but soon there will be also the code to analyze confidence ratings. And I thank you for your attention.
Fantastic. Thank you so much, Pascal.